Hello students, so today we are going to learn this one, the partial differentiation and the gradient. What is exact the gradient is and what do you mean by the partial differentiation? Partial differentiation we are well aware, you can see my videos on partial differentiation here. Let's start with the gradient part. What is the gradient here? So first gradient, we are well aware of the gradient, what we learned before in the earlier classes. We call it as M. No, you know this, it was the basic from those basic mathematics school. The coordinate geometry M comes from slope. The slope is nothing but it was divided by dx, the differentiation. And any tangent, we are drawing any curve, and the tangent to that curve at that particular point, this is going to give you the equation of dy by dx. This was the basics. Now same concept we are going to apply this for a gradient concept, but here the gradient is related to partial differentiation. The gradient is based on the concept of partial differentiation, and that we will be learning now. Let's continue, begin. So see, suppose a gradient. What is the gradient? Gradient is a measure of, what is gradient? Gradient is a measure of how quantity changes. I like to say, just see, gradient. Now this gradient, if I go and make it violent, gradient is a measure how quantity changes over space. The quantity changing over the space. It indicates now what it is changing over the space, and it indicates direction rate of greatest increase. Direction and rate of increase. You know, grade divided is that is rate of increase. It may be increase, it may decrease. Here it is increase. And in mathematics, we often visualize slope of the line or surface. Now in three-dimensional, it will be your surface part here. Okay. So and, what is slope now? In 2D graph, slope, you know, line represents rise or fall. Positive slope, that is what we call it a positive slope here. And the fall, we used to call as negative slope. So this was the basic slope in 2D field. And steeper line, more the line is steep, it is a larger gradient. That was the concept. Now, one more application of derivatives, for example, we have temperature gradient, dT, temperature with respect to time, change in temperature with respect to time there. Okay. So you can also say delta T upon delta T here. This is your temperature, this is your time here. This is related to temperature map, what we call. And would show the direction of how temperature is increasing. Now, the gradient is steepest ascent, always direction of steepest increasing function. What is always gives the steepest increase in the function? How it is increasing? This is the basic. Now let's denote this one. Now this temperature map we just we saw. For example, if you are getting y, the gradient is 2, slope of this one divided by x, the derivative will be 2. Now in this case, this is one of the most important part in your machine learning also. It shows temperature, how direction steepest increase, that is just so. Now more important is machine learning. Gradient descent is one of the important part, which is for optimization algorithm. To minimize the cost function, it indicates direction to adjust parameters and decrease error of model according to some machine learning resources here. This is what the part we are having. We are going to learn. Now, machine representing, mathematically representing. Now, this is related to partial differentiation. We will say that gradient of a function. What is gradient? The gradient of a function f is denoted by delta opposite inverse delta, which is called nabla f, which is vector containing partial derivatives of f with respect to each variable. With respect to each variable, that means with respect to it, with respect to x, with respect to y, all the variables. That is what we call that as gradient. Okay, fine. Now let's go for one example. Now see, if the partial derivatives are fundamentals of multivariable calculus, remember, we denote partial derivatives by DAVA or DO, what was the rate of change of multivariable with respect to one variable while treating other variables as a constant. This is the basics of partial differentiation. Now let's go with this gradient definition. So what is gradient definition? So gradient of a function is defined to be vector field. Generally, gradient of a function can be found by applying vector operator to scalar function, that is delta f of xy. This kind of vector field is known as gradient vector field. For example, now this gradient vector field, we have gradient in two dimension. Two dimension will call it will be a partial differentiation of f of x with respect to I. That will be I or multiple I with that. That is for your x-axis, the unit vector, and partial differentiation with respect to y to j. This is for the two-dimensional gradient. And if you consider three-dimension x, y, z, then three-dimension you can say z-axis also x, y, z there. So x gradient function of xyz, that is nabla f of xyz, will be partial differentiation with respect to x, partial differentiation with respect to y, partial differentiation with respect to z. So x will be multiplied by I multiplied by j for y-axis and k for the z-axis. So this is how we will be taking just partial differentiation and adding. That will be your gradient. Very easy and very simple. Now, now conditions. What are the properties? Okay. Now actually the gradient in any direction defined as rate of change of function is that direction. Now see, component I is the partial differentiation with respect to x. In other words, say that the rate of change of function in x direction by keeping y and z constant. This is how we will call it as directional derivative. We call that as a directional derivative. And now, if one of the important properties gradient should take, that is a scalar function. Now, what are the properties that should be taken into consideration? Now, just so I said, a scalar function is one of the important properties. And f of xy and produces vector function. The the gradient for the f, so nabla f there, gradient. So gradient should take a scalar function. That is function and produces vector. Vector delta f will be your, the gradient will be your vector function. And the function, it is also a vector function, but the gradient should take a scalar function. We will be taking the gradient as a scalar function. Just with the example that will be more clear. Now vector gradient f of xy should lie in the plane. One is another one plane and should be another plane. That is not possible. It should not be there. They both should lie one plane there. Okay. Now see. For example, let's go for one of the examples here. Now see, this is the given part here. F of xy is x square plus 3x minus y square. Now first step is you will be finding partial differentiation with respect to x, f of x. That is the partial differentiation with respect to x. So keeping x square will become 2x and 3xy, in this x is constant, it will be 3xy. The differentiation for 3y, differentiation for x is 1 and this y square is constant minus 0 here. So when minus is not connected to 0 according to basic algebra rules, but I'm just confirming. So this y square, I'll write much better. Otherwise, somebody will ask why you're going against the rules of mathematics. So it did not happen. So this is negative minus 0. The differentiation for y square, that will be 0. So that becomes 3y to 1. So we are getting the partial differentiation this way. Now see, what is the second? Let's go for with respect to y. So f of y will be 3x minus 2y. How we are getting 3x? So x square, the differentiation is 0 since it is a constant. 3xy, the partial differentiation, that is partial differentiation with respect to y. This becomes 3x there. The differentiation for y is 1 here. And differentiation of 2y, partial differentiation 2y. In this case, what will happen here with respect to y? That is, sorry, differentiation of y square. Differentiation y square, that will become 2y there. So we got 3x minus 2 as second differentiation. Now what is the gradient vector form? Delta nabla f of x comma y. So it is written in a vector form, vector f of x, f of y. So this will be written to x plus 3y, 3x minus 2y. This is what we got a gradient vector. This is finally what we are getting a gradient vector. For my next updates, please watch our next videos. Please like and subscribe if you are. If any doubts are there, please send me on your comments. I'll be clearing your doubts. Okay, thank you.